You might remember this thing. It's the Perpetual Wedge that we made in video 2310. Now, this is an example of a general mechanism. In this form, it's not really a lot of use for many things. I mean, you can put it in a pulley and you wrap a rope around that section, but it's a bit cumbersome. However, it does give an impressive gear ratio for a very low number of parts, and it's a very simple mechanism. Now, that really appeals to me, particularly in things like clocks. I mean, you can get huge gear ratios in clocks with marvellous mechanisms. And of course, complexity, or things that look complex, are awe-inspiring. It's a bit like things that are big. But my mind doesn't work that way. I want things to be as simple as I can possibly make them. And here we've basically got three components giving a 100-to-1 gear ratio, which is ludicrous. And in a clock, we need gear ratios like 60-to-1, because there are 60 seconds in a minute and 60 minutes in an hour. So we can get one turn for every 60 turns. That's our clock made. So I'm looking for big gear ratios in the order of 60-to-1 and a simple mechanism. And of course, this won't do the job. But the principle here will, because movement is relative. It doesn't matter if it moves around the outside or it moves around the inside, it's still the same movement. And here we have two moving gears, this one and one fixed gear, this one. This one is one tooth bigger than this one. So every time that makes a rotation, it moves a part of a tooth. Once it's made 100 rotations, it will have made one rotation on the 100th tooth. So we're getting a 100-to-1 gear ratio because 100 turns of this equals one turn of this by nudging it part of a tooth all the way along with this outside rotating gear. This gear doesn't add anything to the gear ratio. It's these two that make the gear ratio. The bottom one is one tooth bigger than the top one, and the number of teeth on the top one is going to be the ratio that you're looking for. So we're looking for something with 60-to-1, so clearly we want 61 teeth on the bottom, and we want 60 teeth on the top, so that every 60 rotations of this, we get one rotation of that. And the other thing that we want to do is we want to turn it inside out, because we don't want it like this. We want it clock-shaped. We want it to move in a circle, because this doesn't move in a circle. This moves in an ellipse. We want to make it certain its movement. And so from that general principle that we've got here, we need to think what we need to do to make it into a specific example we can use in an actual machine. And those are the two things that we need to do. We need to make it internal, so everything's nice and round, and we need to get rid of that ellipse. Okay, so to solve those problems, all I did was turn to Tinkercad and create two ring gears, one with 60 teeth and one with 61 teeth, because ring gears point inwards and spur gears point outwards. I want it inwards, so ring gears it is. Now remember, this bit, the driving cog, plays no relationship, or rather plays no part in the gear ratio. It's only the tooth difference that matters. So we can make a driving cog as big or as little as we like. So I created this, a 54-tooth gear, that will be driven round an ellipse in those ring gears. To do that, of course, I need an ellipse. So I created a big hole, 40 millimeters across in the middle of that gear, and a cam. That cam is driven from a center point, and as it rotates, of course, it acts like a cam. The cam pushes in there and makes that go all the way around the ring gears. So of course what I need to do is print those parts off. Once we get them printed off, there we go. Of course the ring gears do have base plates on them with the central drive hole because the thing needs some structure. This main drive gear slots in there like that, and of course when we drive that cam, that main drive gear is forced to go round and round that internal ring gear. The cam slots in the centre there. Of course there's a drive shaft. The drive shaft goes through, the handle fits on the other side, and then we pop this top on, engaging the gears, and when we engage those gears, the whole thing gets held together with a clip. And once we get it together, that's what we've got. We turn that handle, and this top one will move. There's a black dot on there, and that black dot will move around as I turn the handle in the ratio of 60-to-1. So 60 turns of that dot will move all the way around. And it's an example really of how you take a mechanism that may not look useful to you, make the changes you need to make, because remember, all motion is relative, and you can make it into a mechanism that will be useful to you, given the job you want to do. So I want a couple of these for my clock, but that's how I made the changes from that to that, in order to make this useful in the application I have for it. So when you're looking at mechanisms by themselves don't often seem very useful, but they do a job, and if you understand the job they do, and this one's massive gear reduction, a few parts, you can adapt them into the specific case that you want to do. In my case, a very simple clock, or rather, a clock that works pretty well, but only takes a few parts. Anyway, I thought I'd go through that process of modification. Of course, I was building a clock, but I thought it would be interesting to see that process as a standalone thing. I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.